In this video, I'll be going over fundamental trigonometry identities. Okay, so let's begin. I hope you guys are familiar with sine, theta, cosine theta, and tangent theta. These are the trigonometry basic identities. These also have reciprocal identities, and these are secant theta, or secant u in this case, cosecant u, and cotangent. U is just a variable. It can be theta, it can be x, but for now we're just going to be using u. So secant u can be rewritten as 1 over cosine u. Cosecant u can be rewritten as 1 over sine u. And cotangent u can be rewritten as 1 over tangent u. As you can see, it's the same basic identities, just rewritten in a different form. Always remember that this is how I remembered them, is cosine starts with a C. His reciprocal identity starts with an S. And sine starts with a C. So it's basically inverse, just that's how I memorize it personally. And then for tangent theta or tangent u, his reciprocal is just cotangent, basically in the name, cotangent. So that's how I memorize those. Okay, so the quotient identities is next. Quotient identities is just tangent, as you guys already know. This is sine u over cosine u. And again, we can be using theta, but I'm just using u in this example. Then cotangent is actually just the opposite, which is cosine over sine. Pretty easy stuff to memorize. Now, the Pythagorean identities. These are some identities that are super important, and you'll be using them throughout your trigonometry class. So these are important to memorize. Okay, so our first one is cosine squared theta plus sine squared theta is equal to 1. Our second one is secant squared theta equals 1 plus tangent theta squared. And our third one is cosecant squared theta equals 1 plus cotangent squared theta. So you might be looking at these like, what do these mean? What are these used for? But for a simple introduction, I'm just going to be showing you guys how to use them, how to implement them. And these are important to know and memorize. In certain courses, you won't be given these during a test. So a good way to memorize them is that if you can memorize this one, the basic one, you'll be able to memorize these too, because you can actually derive these. So for example, let's start with the second one. So if we have this one, cosine squared theta plus sine squared theta, you can divide everything by cosine squared. So this works like any other equation. Just if you do something to one side, you must do it to the other side. So here we're dividing everything by cosine squared theta. Here, this first term will turn into 1. This second term is sine over cosine. As we can see, this is tangent. So this would be tangent squared theta. Then this will equal the reciprocal of cosine, which we already saw. The reciprocal of cosine is secant theta, so we can write this as secant theta squared theta. As you can see, we have derived this one right here. Similarly, we can derive the third one if we divide everything by sine squared theta. So, dividing by sine squared theta, we get that this is, we see cosine over sine, this is cotangent squared plus 1, sine over sine is 1, And then the reciprocal of sine, which is cosecant squared theta. As you can see, we have derived these two equations from the first one. So all you really have to memorize is cosine squared theta plus sine squared theta equals 1. And you'll basically have the other ones right there. Okay, so another thing to know is the even and odd identities. Here, we're going to see that cosine negative angle will be equal to cosine positive angle. Then sine negative angle will be equal to sine negative sine angle. And then tangent will be the same as sine. Now the reciprocals, they're the same, so cosine, as you can see, it's positive. So secant's also going to be positive. When it's angle, it's negative. And then same thing with this one, with cosecant and cotangent. So these even and odd identities are basically found on their graphs, and that's how you derive them. I'll link a video down below explaining why these are what they are. Those other videos will do a better job explaining than me, but for now, just know that these are the values of the identities. Okay, so another thing that you might need to know is the complementary angle identities. Again, I'll link a video down below explaining why these are what they are, just because I don't have enough time to be explaining them in this video. But yeah, let's go over them. So sine pi over 2 minus an angle will be cosine u, and I'll just write these down. Again, I'll link a video down below explaining why these are what they are. Okay, so now let's get into verifying identities. So an equation is true under specific circumstances, whereas an identity is true for all values in the domain of each expression. General guidelines. These are some things you would want to know. You want to work with one side of the equation at a time. It's often better to start with the more complicated side first. We'll see this in practice. Look for opportunities to use fundamental identities. Note which functions are in the other sines and cosine pair up well, as do secants and tangents and cosecants and cotangents. We'll see this in practice also. If preceding guidelines do not help, then try rewriting all terms to sines and cosines. When you verify an identity, you cannot assume that two sides of the equation are equal, because you're trying to verify that they are equal. As a result, when verifying identities, you cannot use operations such as adding to the same quantity to each side of the equation or cross multiplication. Again, we're trying to verify an identity and not actually, they're not equal. The equation is not equal, as we'll see in some examples. Okay, so first example, we're going to have to simplify this expression. So what we can do is treat this like any other expression you would in algebra. You can just treat cosines, cosecants, all these identities as terms. So we can see that in this term we have a cosecant, and in this other term we have a cosecant. So we can actually factor this a cosecant out. So we'll have cosecant x, and then we'll be left with cosine squared minus 1. We can factor it. Now, recall our Pythagorean identities here. These, we're going to use this one. So, remember, cosine squared plus sine squared theta equals 1. if we rearrange this, we get that cosine squared theta minus 1 equals negative sine squared theta. And we can use this right here for this term. So we can replace that with negative sine. So cosecant x equals negative sine squared x, like so. Now, recall that this, oh, I did not mean to do that. Recall that this cosecant is actually just 1 over sine. So, one sine will cancel, and we're left with negative sine x. Simple. This is the simplification of this expression right here. Okay, so now we're asked to factor each expression. Like I said, treat this like any algebraic expression. You can just factor out. So what do we realize here? There's a squared term. There's a 1. This is a difference of squares. We can literally rewrite this as 1 plus cosine theta times 1 minus cosine theta. And then we're done. That's it. For the next example, we have 2 cosecant squared theta minus 7 cosecant squared, theta plus 6. So, like I said, you can either solve this with the cosecants there, or some prefer to replace cosecant with an x. Okay, so we can let x equal cosecant. So we will have x squared minus 7x plus 6. And this is just a quick quadratic expression that you can easily simplify by factoring. So, what two terms multiply to 12, add to negative 7? So, we can do 2x minus 4x minus 3x plus 6, because as we can see, 4 times 3, they multiply to 12, positive 12, and then they add to negative 7, as we have here. So this is just simple factoring by grouping, and let's just factor this. So grouping these terms together, and then factoring out the numbers, we can factor out a 2x here. We'll have x minus 2. Then we can factor out a negative 3 here, and we'll be left with x minus 2. Remember, we always need to have these two terms equal to each other. Whatever is in parentheses always has to be the same. And now we can just rearrange this and say that 2x minus 3, because we have a negative 3 right here, multiplied by x minus 2, and that's it. We have factored this expression. Actually, we have factored out for x. Now we just replace the x with cosecant theta. So this is one way we could do factorization identities, but this could just help as practice for a beginner, and then you can just approach any other identity just factoring out with the actual identities. Okay, and we're left with this factored expression. Okay, for our next example, we have secant squared x plus 3 tangent x plus 1. Again, coming back to our Pythagorean identities, this looks like we have a secant. So, in order to get a secant, we're going to have to divide by cosine squared all of these, and we'll have 1 plus tangent theta equals secant theta squared. Okay, so we can replace this secant with this. So we'll have 1 plus tangent squared theta plus 3 tangent x plus 1. And we did this substitution because we want to have like terms. just like in algebra, we want to be able to factor and simplify with like terms, so that's why we replaced secant with this expression. Okay, so just adding like terms, we'll have tangent squared theta. I'm just rearranging this like a quadratic equation to make it easier. So plus 3 tangent x, I said theta, I meant to write x, plus 2. Then we can just factor it out by replacing it with a term, but for now I'm just going to leave it like that. Okay, so what multiplies to 2 and adds to 3? Okay, so that is 2 and 1. So we'll have tangent squared x plus tangent x plus 2 tangent x plus 2. So these two add up to 3 tangent x and multiply to 2 tangent. I just multiplied to 2. Okay, so now we can factor them out by grouping. So factoring out a tangent x, we'll have a tangent x plus 1. Then factoring out a 2, we'll have tangent plus 1. And since these two are equal, we know we've done it correctly, and we'll just write this as tangent x plus 2 times tangent x plus 1. And we're done here. Now on to verifying identities. Okay, so I actually messed up here. This should be a cosine minus x, negative x. Okay, so we need to verify this identity, this expression, with this. So we can't treat this like a regular equation. If we add, let's say 1 here, we can't just add it here. That's not verifying. We need to verify that this equals this. So we can't really touch this. So first, we have to pick a side that we're going to verify. Usually, the most complicated side works better because you can simplify this down to one term rather than having this term expanding the term. It's much easier to condense than to expand. Okay, so to begin, my teacher taught me this, so you want to write where you start. So LHS stands for left-hand side, indicating that we're going to start with the left-hand side of the expression, This will be easier on your instructor and to revise over your work once you're done. So indicate, and if you're starting with the right-hand side, you can always write right-hand side. Okay, so this will set this equal to whatever we're going to do. So looking at this expression, we see that we can factor out a secant x from this expression. And like I said, we only going to focus on the left-hand side of this expression. So factoring out a secant, we'll have 1 minus sine squared x. And now, what can we do to get to this? So we're trying to get to a cosine. And we know that secant is actually just a reciprocal of cosine. So we can rewrite this as 1 over cosine. Okay, good. Now, how are we going to get rid of this sine squared? Well, if you think back to our Pythagorean identities, we know that we can somehow get a cosine out of this sine. And if we move this sine to this side, and we move this 1 to this side, we'll have cosine squared theta subtract 1 equals negative sine squared theta. And we have a negative sine squared theta here. So let's just replace that with our cosine squared theta. Doing so, we'll have 1 plus cosine squared theta minus 1. We subtract these two 1's, these cancel out. Now we're left with 1 over cosine times cosine squared. And we can just remove this and remove one of those. And we'll be left with cosine. Well, I said theta here. My bad. I meant to say x, same thing. Is equal to this right here. And then you might be wondering, that doesn't look equal. Well, if we remember to our even and odd identities, actually, these two are in fact equal, and we have verified the identity. Okay, so next example, we have sine squared x plus cosine squared x all over cosine squared x times secant squared x equals 1. So, like I said, you can't, this is not an equation, so you can't add or multiply anything out. Okay, so we're going to start with the left-hand side because it looks more complicated. Obviously, you can't really do anything with that 1. Technically, you can, but it's difficult. Okay, so starting left-hand side is equal to, we know this is just equal to 1 with our Pythagorean identities. So 1 over cosine squared x times secant squared x. Now, how can we simplify this further? So we want a 1. So technically, we're trying to find a way where we can just simplify this to 1. So we know that another good approach is to turn everything we can into cosines and sines. So our secant can be rewritten as 1 over sine, or 1 over cosine. So cosine squared x equals 1 over cosine squared x. Now, if we multiply these together, we can see that these two cancel out, leaving 1 over 1. And this is equal to 1. And then 1 is simply 1. And we have verified this identity. Okay, last example I'm going to go over is this one right here. Like I've said, we have to pick one side. Which one looks more complicated? This time, the right-hand side looks more complicated. So let's start with the right-hand side. Okay, so what can we do to get to secant squared x? So there's many ways you can attack this problem, but I'm simply going to start with multiplying by the conjugate of each fraction. So we'll do 1 over 1 minus sine x, and then we're just going to multiply by 1 plus sine, because we're trying to get common denominators here, so we can add these two together somehow. So 1 plus sine x, and then we're going to multiply also by the denominator down here. Okay, now that we have common denominators, we can add these two together. These will cancel, and these will add these two ones together. Okay, and we can see that this is simply a difference of squares, so we can rewrite this as 2 over 1 minus sine squared x. And then, what do we know? We have another candidate for our Pythagorean identity. So let me just write this here to remind you guys. If we subtract sine, we'll just have cosine. And we are trying to get some sort of cosine, so it would make sense to subtract to replace this. So if we replace that 1 minus sine squared with cosine squared x, what do we have here? A reciprocal. This 2 is just, this is equal to 2 secant squared x, and we have verified the identity. Okay, so this is the end of the video. I just wanted to go over some fundamental trigonometry identities. If you want to learn more about trigonometry, please go watch my other videos, as I'll be posting more of these covering all concepts of trigonometry. So be sure to subscribe, and thank you for watching.